Jack Jackson. In this video, we're going to review some things that we have studied earlier about the relationship between the derivative, or among the graph of the derivative, the first derivative, the second derivative, and the original function. Okay, so first question is, what do the values of the first and second derivatives tell us about the shape of the graph of the original function? And the answer is that we recall that the y values of the derivative are slopes of the original curve. We also remember that a function has a positive slope on an interval, is increasing on that interval, so the function which has a positive derivative point is increasing at that point. It also turns out that knowing information about the first and second derivatives actually tells us quite a great deal about the shape and features of the graph of the original function. So let's get some specifics here. Specifically, what does the first derivative tell us about the shape of the graph of the original function? And the answer is, the first thing that the derivative tells us the slope of the original curve at each point on the curve, that is the slope of its tangent line. And that tells us the direction of the graph of the original function. Specifically, if the first derivative is positive at a point, then the original function is increasing at that point. In other words, its tangent line has a positive slope. If the first derivative is negative at a point, then the original function is decreasing at that point. That is, its original function has a negative slope tangent line. Now, if the first derivative is positive at a whole interval, then definitely the function is increasing on that interval. Similarly, if a function has a negative derivative on an interval, then that original function is decreasing on that interval. We have to be really careful when we're talking about these things not to say it, because we won't know if it is talking about the original function, the first derivative, or the second derivative. If the first derivative is 0 at a point, then the original function has a horizontal tangent line at that point. We call this a stationary point. And this may be a local extremum. So it's actually a local maximum if the second derivative is negative and the first derivative is 0. It's a local minimum if the second derivative is positive and the first derivative is 0. If the second derivative and the first derivative are both 0, it may be an extremum or it may be an inflection point. We have to investigate further to see which it might be. Should be one or the other, but not both. So you have to figure out which one it's going to be. If a function has a local extremum at a point, then the derivative has to be either 0 at the point or undefined, or it is at an endpoint. So those are sort of the only places you can have a local extremum, at least what I'm calling a local extremum. I have seen some textbooks that only call a local extremum a place where the derivative is 0. I prefer to use a more general definition that says a local extremum is, let's say, is either a local maximum or a minimum, whereas if you could look at the x's nearby, say draw a circle around the point, and it's the lowest point in that little neighborhood, that would be a local minimum. If the derivative is defined at a point, then the graph is continuous, one connected piece, no breaks of any kind. It's also smooth, so it has no sharp corners and no vertical tangent lines near that point. So if we zoom in near the point on the original graph, it will look approximately like the tangent line, which is a non-vertical line or a linear function near that point. So that's a feature we call local linearity. So what does the second derivative tell us about the shape of the graph of the original function? Again, we want to try to be as specific as possible. The second derivative tells us the concavity of the original function. The first derivative is the rate of change in the original function. The second derivative is the rate of change of the the original function. So it turns out if the second derivative is positive at a particular x value, then the first derivative is increasing at that point, and the original function is concave up at that point. If the second derivative is negative at a point and the first derivative is decreasing, the original function is concave down at that point. If the second derivative is 0, then the original function may have an inflection point. Not guaranteed, however. If the first derivative is non-zero and the second derivative is 0, then the original function definitely has an inflection point at that point. On the other hand, if the first derivative and the second derivative are both 0, as I said earlier, the original function has either a local extremum or an inflection point, but we don't know which it will be without a little bit further investigation. turn that around sort of the other way. If the original function has an inflection point, then the second derivative is 0 or undefined at that point. So here's an example. We're going to look at a graph here in just a second of a polynomial function where f of x will be given in red. The graph of its first derivative is in green, and the graph of the second derivative is going to be in purple in this particular example. And so you'll see some of these things that we talked about. Let's just look at the picture and you can see it. So the original function is the red one. The first derivative is the greenish one here, and the purple one here is the second derivative. This is a polynomial. I believe this is a fourth degree polynomial for the red one. Notice it must be at least degree 4. It has to pass, crosses the x-axis. It looks like -4, -1, 2, and 3. So it's probably x plus 4 times x plus 1 times x minus 2 times x minus 3, perhaps times some number, and that some constant, and that gives you this graph. So then its derivative will be a third degree polynomial, which you see here, and the second derivative will be the purple quadratic polynomial. Take another derivative. The third derivative would be a line, and the fourth derivative then would be a constant function, and the fifth derivative would and higher would be the x-axis. Y equals 0. All right, so let's just look at these right here and see if we can tell something about the relationships among the graphs. If you've been following along with all my videos, you've seen things like this many times already. We've looked many times at these relationships here, so this is sort of just a review. Notice here the far left, it looks like the original function is decreasing, so that means the derivative is negative, which you see right here. The derivative hits 0 right here, looks like -2 point something, maybe 2.9 or 2.8, something like that. And then down here is where we have a minimum on the original function. Then the derivative goes positive, and so that means that the original function is increasing, which it does all this time from that x-intercept there on the derivative over to this one here at about, oh, maybe that's 0.4, 3 or 4 or something like that. At that point we have another local extremum. This time it's a local maximum on the original function. Then the function decreases to a local minimum down here. Meanwhile, the derivative is negative. Where the derivative hits 0 is where the minimum occurs, which is right about there, 2.5 something or 2.6, something like that. Now, notice that the derivative, it is also increasing here. That's going to be when the second derivative is positive and the original function is concave up. Okay, between these places, so right here where the second derivative touches the axis, that x value is going to be where we're at a maximum on the original function. They're about -1.6 maybe. And right in there at the same x value is going to be where the original function has an inflection point. Original function has the inflection point. Second derivative is 0. First derivative is non-zero, but the first derivative has an extremum. So here we have another extremum over here on the first derivative. Second derivative is equal to 0, and the original function has an inflection point right there, maybe 1.6 or so. Okay, so it shows you some things there. Now, we've already looked at these kinds of ideas many times, so let's move on just a minute. And so what we want to do now is we want to combine everything that we've done so far. So this is going to include pre-calculus, everything we know about different classes of functions and what their graphs look like, how to deal with things like order of operations and basic operations like add, subtract, multiply, divide, powers, roots, and so forth, and also things like absolute value and logarithms and exponential functions and different combinations of these things, trig functions, and all this stuff that we know from trigonometry about those. We're going to combine that with the things that we know about calculus, things about how to take limits. Now we know how to use L'Hopital's rule if that's necessary. We know some other techniques for finding limits. We also know how to find the derivative formulas. So we can compute a derivative and a second derivative. We know how to solve equations, or at least approximate solutions to equations using a calculator or Newton's method. And we want to put all of these things together, and our knowledge of the derivative and the second derivative and all this, we put it together, and we want to be able to analyze functions. We also want to do this in conjunction with being able to graph these functions and look at their graphs and tables in, say, a graphing calculator or computer program. Now, what kinds of things are we looking for? Well, things about the function that we might be interested in are domain and range. If it has any endpoints, we want to identify those, although it may go on forever. But if it has endpoints, we want to get them. It might have an isolated point. We might have a little point where we could draw a circle around it, and it's the only point in that little circle. That happens sometimes, not always. Certainly that would be a discontinuity. Any type of discontinuity, whether we have a hole in the graph, for example, or maybe a vertical asymptote, or some other jump discontinuity, or any other kind of discontinuity. Not only vertical asymptotes, but we're interested in behavior. So we're looking at horizontal asymptotes, or maybe oblique, or you might know them as slant asymptotes. We want to know about where the function is reaching extreme values, local and global extrema, both maxima and minima. We want to know inflection points as well. Now, we might also identify whole sections of the graph, little intervals on which the graph is, the original function is increasing, or maybe it's decreasing, or maybe it's constant on a particular interval. Or again, whole sections of the graph where the function is concave up, or maybe it's concave down, or perhaps linear. We want to find any places where the derivative is undefined, if it may be defined everywhere, but if not, tell me where the derivative is undefined. Anything about symmetry. Does it have any kind of reflective symmetry, maybe x-axis symmetry or y-axis symmetry, or maybe symmetry about some other line? And we are also interested in, say, rotational symmetry. Does it have symmetry, 180 degree rotational symmetry about the origin? We call that origin symmetry, or some other similar kind of rotational symmetry. Or perhaps a translational symmetry. We call that periodic behavior. Okay, so periodicity. Does the function have a period? Like trig functions, for example, typically have periods. And then we want to maybe make a table of values, some kind of representative table of numbers, and identify some patterns we might see in that table. We definitely want to make a representative graph, probably with technology, showing interesting features. Sometimes one graph will show all of the interesting stuff that you would like to see in one particular picture. Other times that we will have graphs where you can't see the whole thing in one picture. We might need 2 or 3 or 4 graphs to see the different picture. We might want to graph another graph that has the original function, its first derivative, and its second derivative, and we can see how these things relate to each other. And finally, we might look for families of functions which are defined in terms of some parameters, maybe letters A, B, C, D, whatever, where these letters, we don't know what they are, but they're considered to be some constant. They're unknown constants, but they are constants. Those are called parameters. And we might say, well, what happens if we change these parameters? What happens to the graph of the function? Okay, so we may look at that. I think that we're going to stop here for this video. The next video, we might look specifically at some general characteristics of polynomial functions, and then look at an example of polynomial functions in that video.